Hello and welcome everyone to Science Era. In this video, we are going to discuss gases. What are gases? And I will be using OpenText Chemistry 2 ebook, which is covered by UNISA also. It's very helpful for students who are doing CHE 1501 module from UNISA. So let's begin. For the test questions, from this topic, they can ask you five different questions related to these topic, which can include fundamental physical properties of gases and how they are evaluated. Physical properties may include pressure, volume, temperature, and amount. They can test you on properties of gases and how they are correctly calculated using ideal gas law. So we're going to discuss ideal gas law, properties of gases, then we're going to look at standard temperature, pressure, its definition. We're going to come across different concepts like mole, mass, volume, temperature, density of gases. I'm going to explain them and will show you how they are calculated. Lastly, we are going to look at the partial pressure. So, properties of gases. A gas has no definite shape or volume of its own. It acquires the shape of the container. Why? Reason is that the intermolecular attraction is the weakest in gas, whereas intermolecular separation is the largest. Hence, molecule in a gas moves very fast and gas expands to fill all the spaces available. Properties of gas number 2. A gas has no surface of its own. Why? Because molecules escape from an open container. Third point is a gas is not rigid and is easily compressed. Reason is that intermolecular separation is very large in gases state, which can be decreased by applying pressure. A gas can diffuse into another gas. Reason is that molecules in a gas move very fast, hence the speed of diffusion is very large. Fifth point we have is that a gas on a cooling changes into liquid state. So when we cool down gas, it changes into liquid. Why? Because reason is that cooling reduces the intermolecular separation and increases the intermolecular force of attraction. Lastly, gas can flow in all directions. It requires a vessel closed from all the sides. Next is behavior of gases and kinetic molecular theory. So, ideal gas. Ideal gas have mass but negligible volume. In constant random straight line motion. They work in constant random straight line motion, not subject to attractive or repulsive force. Gas particles collide with each other and the wall of their container, where a transfer of energy between particles may occur, but there is no net loss of energy. Collision are said to be perfectly elastic. Kinetic molecular theory and pressure. Gases exert gases exert pressure by colliding with walls of a container. Volume occupied by an ideal gas is essentially the volume of its container. The greater the number of gas particles, the higher the pressure. Example, adding too much air to the balloon. Pressure and number of gas particles are directly proportional. Pressure and force. When gas molecule collides with the wall of a container, they exert a force on it. This force is known as pressure and it is defined as force per unit area. The standard unit for pressure is pascals, PA, where 1 pascal is equal to 1 Newton meter squared. However, units such as torr, millimeter, mercury, or even atm is frequently used, and you must know how to convert these units from one another. So, atm. Atmospheric pressure is pressure exerted on an object due to the weight of the column of the air above it in the atmosphere. A barometer is a device used to measure atmospheric pressure. Next, we have units of pressure. As I said before, pressure can be measured using torr, millimeter, pascals, atm, and etc. So, pascals is the SI unit, a standard unit for the pressure, which is equal to 1.0 Newton meter squared. Newton applied to an area of 1 meter squared. Millimeter or mercury is a common unit of the pressure that is based on the height of a column of a mercury will rise due to the atmospheric pressure at sea level. Torr is equal to 1 mercury. atm is equal to the pressure exerted at sea level by the air in the atmosphere. Pounds per square inch is equal to the pressure caused by 1.0 pound of force exerted on the 1.0 square inch of area. Pressure laws. Standard temperature and pressure is a set of standard conditions agreed upon around the world and is equal to 1.0 atm pressure and a temperature of 0 degrees Celsius. If experiments are always conducted under the same conditions, comparisons can be made between different sets of data. Standard temperature and pressure is a standard set of conditions which has been defined for such experimental measurements. So, standard condition corresponding to STP are pressure equal 1 bar equal 100,000 pascals equal 100 kPa. Temperatures equal 0 degrees Celsius, which is equal to 273.15 Kelvin unit, or 0 degrees Celsius. Dalton's law of partial pressure states that the total pressure exerted by a gas mixture is sum of partial pressure of the component of gases. So, you have given three cylinders. If equal volume cylinders containing gas A at a pressure of 300 kilopascals, gas B at a pressure of 600 kilopascals, and gas C at a pressure of 450 kilopascals are all combined in the same cylinder, the total pressure of the mixture will be 1350 kilopascals. So this is how we apply the Dalton's law of partial pressure. Gas laws. We describe a relationship between gases, relationship of pressure and volume between gases using Boyle's law. Boyle's law states that the volume of a fixed mass of a gas at a constant temperature varies inversely with its pressure. So P1 V1 will be equal to P2 V2, where P1 is the pressure 1, V1 is the volume 1, P2 is pressure 2, and V2 is volume 2. Pressure and volume vary inversely. As volume decreases, pressure increases. Temperature and number of particles are held constant in Boyle's law. So let's look at the example. Here on the screen I have one example. We're going to solve it using Boyle's law. A sample of oxygen gas has a volume of 150 ml when its pressure is 0.947 atm. What will the volume of the gas be at a pressure of 0.987 atm if the temperature does not change? So, first we're going to look at what information is given to us in the question. We are given pressure 1, We are given volume 1, we are given pressure 2. What we are looking for is volume. So using P1 over V1, uh, pressure 1 times volume 1 equals pressure times over volume 2 equation. We're going to substitute all the given data and then solve for V2. Next we have Charles' law. Charles' law describes the relationship between volume and temperature. It states that the volume of a fixed mass of a gas held at constant pressure varies directly with its Kelvin temperature. So, as the temperature increases, volume increases. Temperature is directly proportional to the volume and it is kept constant. Pressure is kept constant. So Charles law equation for Charles law is V1 over T1 equals V2 over T2. V1 is the volume 1 and T1 is the temperature 1. V2 is volume 2 and T2 is temperature 2. Let's look at the sample problem. A sample of a neon gas occupies a volume of 752 ml at 25 degrees Celsius. What volume will gas occupy at 50 degrees Celsius if the pressure remained constant? So they gave you the volume 1, which is 752. They gave you the temperature 1, which is 25 degrees Celsius. They gave you the temperature 2 also, which is 50 degrees Celsius. What we are looking for is volume. So we're looking for V2. We're going to substitute all the given data in this formula V1 over T1 equals V2 over T2 and then solve for the unknown. Third law, third gas law, Gay-Lussac's law. It describes the relationship between pressure and temperature. It states that the pressure of a fixed mass of a gas held at a constant volume will vary directly with its Kelvin temperature. So pressure and temperature have direct relationship and in this case volume is kept constant. So pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. Let's look at the example. The gas in an aerosol can is at a pressure of 3 atm at 25 degrees Celsius. The can wants not to allow the temperature to get above 52 degrees Celsius. So they have given you pressure 1, which is 3 atm at 25 degrees Celsius. They given you temperature 1, which is 25 degrees Celsius. They given you temperature 2, which is 52 degrees Celsius. They're asking you what would the pressure of a can be at 52 degrees Celsius. Remember when solving for when you are given temperature in degrees Celsius, you're going to change degree Celsius into Kelvin and then solve for pressure. In order to convert Celsius to Kelvin, you're going to add 273 to the given temperature, which is in Celsius, to convert it into the Kelvin scale. Substitute all the given data into the formula and then solve for the unknown. So here we have summary of the gas laws. We looked at Boyle's law, Charles' law, and Gay-Lussac's law. So when looking at Boyle's law, we saw that pressure increases as pressure increases, volume decreases, and we knew that temperature and number of particles are kept constant. In Charles' law, we saw that volume increases. As the volume increase, temperature also increase when the pressure is constant. In Gay-Lussac's law, as pressure increases, temperature also increases when volume is kept constant. This brings us to the combined gas law. The combined gas law expresses the relationship between pressure, volume, and the Kelvin temperature of a fixed amount of gas. P1 V1 is over T1 is equal to P2 V2 over T2. Let's look at the example of combined gas law. A sample of nitrogen gas has a volume of 0.180 liters at a pressure of 0.800 atm and a temperature of 29 degrees Celsius. What is the new temperature of the gas at a volume of 90.0 ml and a pressure of 3.20 atm? We are given pressure 1, which is 0.8 atm, pressure 2, which is 3.20 atm, V1, which is 180 ml, V2, which is 90 ml, and T1, which is 302 Kelvin units. We are going to solve for temperature 2. So T2 will be equal to 288 over 0.477, which is equal to 603.8. They ask you to solve for temperature in degrees Celsius. In order to convert Kelvin units into degrees Celsius, we're going to subtract 273 from from the answer we calculated, which was 604 minus 273 will give you 331 degrees Celsius. Ideal gases versus real gases. Kinetic molecular theory explains the behavior of gases using ideal gas as a model. Real gases, however, do not follow this. Ideal gas always behave as predicted. They have negligible volume, no attractive or repulsive forces. They move randomly in a straight line. They are perfectly elastic collisions. Real gases, attractive forces cannot always be disregarded. Water vapor molecules attract one another to form rain or snow in atmosphere. Volume of gas particles are negligible under high pressure. Ideal gas. We are going to assume that gases behave ideally. In other words, they obey gas law under all conditions of temperature and pressure. An ideal gas does not really exist, but it makes the math easier and is a close approximation. If the pressure is not extremely high and if the temperature is not extremely low, many gases approximate the behavior of ideal gas. The ideal gas equation will give us values of pressure, volume, number of moles, and temperature, which are close to the true values. Let's look at the equation of ideal gas. Ideal gas law states that PV equals nRT, where P is the pressure. Typical units are atm or torr or mercury. Volume, V is equal to volume. Typical units for volume is liters. N is equal to number of moles. T is temperature, which must be in Kelvin. If you are given temperature in Celsius, you're going to subtract 273 to convert it into the Kelvin. Um, R is equal to the gas constant, which is 0.0821 liters atm per mole Kelvin. Gas constant R. In ideal gas equation, the term R is called universal gas constant or simply the gas constant. R is equal to 0.08206 liters atm mole per Kelvin. The way R is expressed depends on the unit of pressure, volume, temperature, and number of moles. If, for example, we are working with pressure in atm, volume in liter, amount in mole and temperature in Kelvin, then R is expressed as 0.08206 liters atm mole per Kelvin. However, if we are working with pressure in kilopascals, volume in liter, amount in mole, and temperature in Kelvin, then R is expressed as 8.314 liters point kilopascals point mole per Kelvin. Gas densities and molar mass. The density of a material is defined as its mass divided by its volume. When calculating density, we calculate density using D equals m over V formula, and molar mass as molar mass is equal to D R T over P, where D is the density of gas in grams per liter. R is the gas constant, T is temperature, and P is pressure. Example of density and molar mass. A 2.10 liter vessel contains 4.65 gram of gas at 1 atm and 27.0 degrees Celsius. What is the molar mass of the gas? Using the molar mass formula, which is equal to dRT over P, we're going to substitute all the given data. Before that, we're going to calculate the density using mass over volume. They have given you mass of the gas, which is equal to 4.65 gram, and volume, which is equal to 2.10 liter. So mass divided by volume will give you 2.21 gram per liter. When calculated the density, you're going to substitute R, which is constant, gas constant, D, we calculated density, temperature, which is 300.15 Kelvin. You're going to convert 27.0 degrees Celsius into Kelvin by adding 273 into 27 and divided by 1 atm, the pressure unit given in the question, will give you the molar mass of 54.6 grams per mole. Next we have is Dalton's law of partial pressure. Dalton's law states that the total pressure of a mixture of gases or vapor is equal to sum of partial pressure of its components. For example, sum of pressure that each component would exert if it were present alone and occupied the same volume as the mixture of gas. So here in this diagram given on the screen, pressure 1 in the container 1, pressure 2 in the container 2. So using Dalton's law, we're going to sum the total pressure, which is P1 plus P2. Using the formula PV equals nRT, you're going to calculate pressure of cylinder 1 and then going to calculate pressure of cylinder 2. Next, a partial pressure and mole fraction. The mole fraction of a gas in a mixture of gases is defined as X equals N over Ng over Nt, where Ng or N1 is the number of moles of gas 1 and Nt is the total number of moles of all the gases in a mixture. The mole fraction is a dimensionless number without units because it tells you what fraction and amount of a particular gas occupies in a mixture of gases. The partial pressure of a gas can be related to the total pressure by the equation Pa equals XA PT or X1 PT, where X is the mole fraction and PT is the total pressure. So here I have an example of Dalton's law of partial pressure. A sample of natural gas contain 8.24 moles of CH4 and 0.421 moles of C2H6 and 0.116 moles of C3H8. If the total pressure of gases is 1.37 atm, what is the partial pressure of propane? So they have given you the total pressure and they have asked you to calculate the partial pressure of propane. So in order to calculate the partial pressure, we're going to put propane on top, which is equal to 0.166 moles, and then total pressure, we're going to add all the number of moles of or given in the question, which is 8.24 plus 0.421 plus 0.116. So this will give you the PT, and then pi x is the propane, pi is the amount we are looking for, right? So when we calculate for x, we say 0.0132 times 1.37 atm will give you 0.0181 atm partial pressure of propane, which is C3H8. So now we are at the end of the gases section. If you like my video, please do subscribe, like and share. Thank you.